Hello, this is Mr. White, and this video is on antiderivatives or indefinite integrals part 2. Here are the two exercises for today, a dreaded trig integral as well as an exercise in which we find general and particular solutions. Let's get to the trig integral. And one of the things that makes trig so difficult to deal with is just the fact that there's no recipe that works 100% of the time. We just have to have a collection of skills and be willing to try them and be willing to fail and then turn around and try a different route. So I'm wondering if anything jumps out at you, the student, as you look at that expression. I'm looking at this, and we've seen enough of our difference of squares pattern to know that that often helps us out. So let's just see where that leads us. And if I FOIL out those two binomials there, I'll get 1 plus sine x minus sine squared x. And hopefully that looks familiar to you. That, of course, is our Pythagorean identity staring us in the face, right? And so now we have 1 over cosecant x, and that 1 minus sine squared becomes cosine squared of x, according to the Pythagorean identity. Now later on, when we learn some more advanced anti-deriving techniques, we'll have other possibilities, other options of where we could go with this. But for right now, we don't have a lot of tools other than to consider all of our trig derivatives, which you really should know really well by now. I'll bring them onto the screen, but again, these should also be engraved in your brain by now. And we ask the question, is this expression that we're supposed to antiderive equal to any of these trig derivatives? Well, clearly it's not going to be these simple sine x and cosine x. If this cosecant weren't here, we'd have 1 over cosine squared x, which would just be secant squared x, right? But unfortunately, that's not the case. So cross that one out. And if it's not immediately obvious where this is heading to, let's just play around with our integrand, as it's called. This is over here is called the integrand of the overall integral. Now let's play around with it. Let's keep in mind some of our fundamental trig identities from yesteryear. We see a cosecant x on the bottom, and we know that cosecant is the reciprocal of sine. So we know that can also be brought to the numerator in the form of sine x over cosine squared of x. Well, still doesn't, at first glance, appear to be very helpful when we look over here. So we just, again, are willing to play around a little bit more with trigonometry, and we see a sine over cosine. And yes, it's cosine squared on the bottom, but I can certainly separate that out and say, I wonder if this will do anything, making it sine over cosine. And what about that fact that it's cosine squared on the bottom? I suppose we could do that. And now we look again at our table, or again, this table which really is in your head, of course, and we're starting to see something. We see that sine over cosine x, that's just tangent of x. 1 over cosine x, well, that's just secant x. And aha, there it is. So we know that what we're trying to antiderive is the derivative of secant x. So when I do the antideriving, the integral symbol and the differential go away, and we end up with just secant of x. And don't forget the plus c. That is our answer. Okay, so recall that the key here to this exercise was knowing your trig derivatives really well, and also just recalling all those trigonometric identities from pre-calculus. All right, let's go on to the next exercise. We are to find the equation for some function of x, some function y, with the given information and the indicated point on the curve. So we're told what the second derivative of y is. We're told what the first derivative is at a certain point. And we're also looking at the picture, and we see that there are some point coordinates that this function y better pass through. I will point out that all this information could have been presented in a slightly different way. This is totally valid, but you also might see this instead. F double prime of x equals 3 minus x. That is exactly the same statement as that. And as far as this other statement, that would be f prime, but not of x, of 2 equals 5. And again, f prime of 2 equals 5 is exactly the same as saying dy over dx at x equals 2 equals 5. So however you choose to look at it, we're going to start by anti-deriving this. And the game plan is, if you anti-derive the second derivative, that will give you the first derivative. And then we'll take that first derivative along with this and anti-derive it and give us the actual function y that we're looking for. All right, so I'm going to erase this alternate form here. And let's start with this. If I anti-derive the left side, I will also anti-derive the right side. And anti-deriving the second derivative on the left will simply give me the first derivative. And anti-deriving 3 minus x, well, whose derivative is 3 with respect to x? That would be 3x, right? And whose derivative is minus x? That would be, since that's x to the 1 power, the antiderivative would involve an x to the 2 power, which means there'd be a 1/2 in front and a minus sign. And let's not forget the plus c. Definitely pause at this point if you need a moment to just ensure that you agree with that. Okay, and I'm going to give this c here a subscript. I'm going to call it c sub 1, just in anticipation of the fact that we're going to have another plus c coming up a little bit later. But let's notice that this is telling us a general expression of the first derivative, and we want to find the particular solution. And this is the piece of the information that's going to help us do it. This is what's going to allow us to figure out what that plus c is. So let's go ahead and plug in the x equals 2. And according to this statement over here, dy over dx at x equals 2 is going to give us just a 5 on the left-hand side, right? And on the right-hand side, I'll plug in the 2. 3 times 2 will give us 6, minus 1/2 times 2 squared, or 4. That's going to be minus 2, plus c subscript 1. And that one's easy enough to do in our heads. We can just solve for c in our heads and tell that c subscript 1 is going to equal 1. So we'll scroll down a little bit, and now we know that dy over dx equals 3x minus 1/2 x squared plus, and we just solved for c1, 1. And if you're at all like me, you'd rather just put this quadratic in standard form here. So let's have negative 1/2 x squared plus 3x plus 1. All right, now that's the first derivative. As far as finding the first derivative of y, and if we want to find y itself, well, we will anti-derive again. Integral with the dx on the right, and the antiderivative of dy over dx will be just y. And on the right-hand side, I anti-derive again. Again, I like this approach of covering up the constant and focusing on the x squared. And so if I anti-derive x squared, it's going to be x cubed. I need a 1/3 out in front to balance it out. And then I unveil and I get that negative 1/2 still sitting out in front. So negative 1/2. Okay, I cover up the plus 3 and anti-derive just the x. That's going to give me x squared. I need a 1/2 out in front to balance it out. And then I unveil and I get plus 3. And when I anti-derive the plus 1, I just get plus 1x. And don't forget the plus c. It's a different c than we had earlier, so I'll call that one c2. Now this, with the c value, is what we would call the general solution for y. And the idea is that depending on what the c value is, a changing c value could cause this graph to either go up or down. It's a vertical translation, and remember that from pre-calculus, that adding a constant at the end of a function, whether it be positive or negative, will cause the graph to go either up or down. So that's our general solution, but we want the particular solution that goes through that given point right here. So we want the particular solution that goes through 1, 3. So once again, we're going to plug those coordinates in to find out what the c value is to give us the particular solution. So focusing on the fact that x was 1 and y is 3, we'll plug in 3 for y equals, let's go ahead and make that negative 1/2 times 1/3. Let's make that negative 1/6 times x cubed, which in this case is 1 cubed, plus 3/2 times 1 squared plus 1 plus c2. We could tell that in order to solve for c, we're going to need to do some common denominators. So I see a 6 and a 2 as my denominators. So let's make 6 the common denominator. That means I'll have 18 over 6 on the left equals negative 1/6 times 1 cubed is still negative 1/6. And then I'll, again, multiply by 3 over 3 here, and that's going to give me plus 9 over 6 plus 1, which is going to be 6 over 6. That was this one right here. And then plus c2. All right, so over here, I've got 14/6. If I subtract it over to the left, I'll end up with 4/6, which is the same as 2/3. That's what equals my c2. So if I scroll back up a little bit to see my general solution, shrink this down a little bit, I'll now write my particular solution. And that's basically the same thing as the general solution, but with the c value plugged in. So negative 1/6 x cubed plus 3/2 x squared plus x, and then plus the 2/3 that we just solved for. That's our particular solution, and we'll put a box around it. And I'll leave the check mostly up to you, but we could at least mentally or on paper check. Go back up to the top. We could verify that when we derive that answer twice, we get 3 minus x. If I derive it once, or take the slope at x equals 2, we'd get a slope of 5, a tangent slope of 5. And we could verify that plugging in 1, 3 does satisfy this equation. So there is our answer.